Um, Welcome to the course VLSI Physical Design Automation. In today's session, we are going to discuss about graph search algorithms. So, where we try to understand what are the conventional graph search algorithms are available, through which how we can able to explore the graph and also the vertices which is existing to be visited or not. So in that there are two types of graph search algorithm we are going to see it in the today's class. One is DFS, depth first search algorithm. Next is BFS, breadth first search algorithm. So these two algorithms mainly we talk about as search algorithms, graph search algorithms, means the output of these algorithms will provide you whether we visited all the nodes which is present in the graph or not. Okay. So these algorithms will never provide any shortest path of these nodes. So this algorithm will be adapted only to explore whether we are visiting to all the nodes or whether we are exploring all the nodes which is present on the graph or not. That is the main fundamental usage of this DFS as well as BFS algorithm. So when we look into it very closer, so by which this DFS and BFS, we can systematically follow the edges of the graph to visit the vertices of the graph which is already existing. So through which we can able to confirm whether we have all the blocks are available or all the vertices are available in the graph as it is which we want to explore. If I want to compare or if I want to keep this algorithm into a VLSI physical design, where we have studied one steps called partitioning in the VLSI physical design flow. So partitioning is the step where at which we are dividing the complex circuit into multiple partitions, where we are name it in terms of modules. We used to call it as module A, module B and so on. We can classify into what? N number of modules. Once you classify it into n number of modules, what happened? That entire circuit into a group of small circuits or sub-circuits. So while we want to proceed further in the VLSI physical design flow, we want to make sure that whether all the partition blocks are available or not, or all the segregated portions of the circuits are available or not, that we can able to confirm by means of these search algorithms. So I can able to assume that every module here has a node or vertices for the timely concerns to understand these graph search algorithms, so that we can able to explore all the modules are available, which all the modules are available according to the partition or not, that we can able to get explored by means of using this DFS or the BFS. So these two are one of the most fundamental and as well as the conventional algorithm which is majorly playing a vital role in order to searching all the vertices which is available in the graph. So accordingly, in today's class, let me just try to explore one by one. So in first case, we just try to explore what do you mean by depth first search algorithm, or in other terms we used to say DFS. So as we said, an algorithm, what is an algorithm? The algorithm will have some certain rules to follow in order to get your desired output. Accordingly, this DFS has to follow 4 steps of procedure. In step 1, we try to see that create a stack to keep track of vertices to visit. Means in this case of DFS, we are going to make use of stack as our data structure, and through each stack we just try to explore whether are we visited all the vertices which is available in the graph or not. The property of a stack is nothing but last in first out. That is what the property of the stack. So the so-called last vertices what we have is going to be available in the stack will be explored well, and it is going to leaving the stack out as first. So that is called last in first out. In second step, we are just doing that finalize the starting vertex. Actually, when the problem is given for us, we have to see that whether the starting vertex is defined in a problem. If the starting vertex is not defined in a problem, so we can able to assume that what we want to start with it, which vertex we want to start with it, accordingly we can able to assume that a starting vertex and proceed further. So we should finalize the starting vertex, and once we finalize the starting vertex, the finalized starting vertex must be pushed into stack. So once the stack is going to be seeded with your initial vertex where we want to start our search algorithm, and from that point we want to follow this procedure until the stack is become empty. Okay, so if the stack is not going to become empty, then we should do the following activity in the step 3. One is, if the vertex on the top of the stack has having any kind of unvisited vertices. Yeah, so if there is any unvisited vertices are available according to the vertex which is available in the top of the stack, so we should push that particular unvisited adjacent vertices into the stack. So in case if there is no visited adjacent vertices are left on the current vertexes, then pop it out from the stack, and then we can move on to the next stack available vertices and see that is there any kind of adjacency vertices are available or not to explore further. So we can repeat this step 2 and 3 until the stack is become empty. So what is the meaning of stack is become empty? When the stack is become empty, it is indirectly indicate that we have visited all the vertices which is available on the graph. So that is what it is used to say that. So in the DFS, one of the major thing is nothing but once we started with the starting vertex, and it will be move onto the depth level of that particular vertices wherever it is possible to explore, and after that it is tracked back to go for the next level of searching. And let me take one sample problem in order to understand this. So let me take a sample problem. Of DFS. Let me take a sample problem of DFS, and let me just take this particular graph, and I assume that this is A, this is B, this is D, this is E, So this is what the example graph we can take it for the DFS for the today's discussion. So according to this particular graph, we can able to easily understand that this graph is comes under the category of a directed graph, and where we can able to see that there are 5 nodes are available, or 5 vertices are available, starting from A to E, A, B, C, D, E. So this is capital E we can say, right? This we can say capital E. So total 5 vertices are available, and also there are some directions are given over here to realize that from A to B or B to D, what in which direction that vertices are is going to be getting connected through which the edges, directed edges. So for this we have to identify that how we can able to form a stack, or how we can able to solve this particular graph, given graph by means of using the DFS, depth first search algorithm actually. Okay. So in DFS there are two time we are going to follow. One is nothing but D time. We have two types of timing scale, timing cycles are available. One is D time and next one is nothing but F time. Okay. So D time is indicating that this is indicating the discovery time, means the time at which we are identifying that particular node, and F time is nothing but finishing time, that means in which cycle we are going to complete that particular node to be get completed, or we are just assuming that the particular vertices is get completed after visit. That is what the F times talks about. So these two are more important when we talk about this DFS. So as we said early in the previous slide, the DFS is going to follow a stack. So we will just always will have a stack over here. So initially the stack is become empty because we not yet started with the any nodes to be get visited. So we can say that your stack is become empty and it is not filled with any vertices. So according to the steps, which is steps and procedure which is given for the DFS, we have to see that is there any kind of source node is going to be given in the problem. If it is not given, we can able to assume that what is the source node. So here, so we are assuming that the source node is going to become A. So let I take a different color for to fill it out. So let I assume that I am just starting with A. So on first cycle I am starting with A. So I am updating here the stack with A over here. I am just visiting A first. So the discovery time of the node A, I am writing that in first cycle I have discovered A, but I not yet completed that the A is visited. So the A is visited means we have to close with the finishing time. Okay, so from A there is a three possibilities available for us to move on. One is the possibility to move on in the three directions here. One is the possibility to move from A to E according to the direction, or there is a possibility to make a move from A to B, or there is a possibility to make a move from A to D. So there are three paths are available to since we are starting from A. So there is no constraints for us to be limiting us to stop us, limiting us to be selecting any one of the path, any of the path. So you have a full freedom to choose which path you would like to have a travel. So based on the travel path, this discovery time or the finishing time is going to be getting changing between one vertices to the another vertices. So accordingly I am going to choose here in this particular given problem, I am just choosing this particular path instead this two path. So it doesn't mean that you should not this two path, even you can select this path or even can select this path in whatever the way you would like to proceed forward. So in this one I am going to start with this A to B over here. Let I assume that I am just going with A to B. So that the discovery time of the B, that next to A I am just visiting to B, the discovery time of B is 2. I am updating the stack with B. Okay. So now what is the stack, what is the rules and regulations says that once you visited the B and see that is there any unvisited vertices available from B, I am just checking that is there any unvisited net is available from B. Accordingly here also there is two paths available, one I can go to B to C, the another path is nothing but I can go to B to D. So I can choose any one. So I am going to choose, I am going to visit B to D. Accordingly I am just updating my discovery time, or discovery time cycle is nothing but 3 for D. I am just updating the same over here, stack with D. Okay. So once you updated the stack with D over here, so what we can do, we can able to see that from D where we can visit. Again there is a two possibility of visiting from D is nothing but one is C and next one is E. So in this case I am just assuming that I am going to visiting with E, so that I am writing that my discovery time of E is nothing but in fourth cycle I am visiting the E, and the same I am updating with the stack is nothing but E over here. So once I have visited E, so after that from E where we can go back, I can just go is nothing but to B. I can go to B, I can done when in fifth cycle. But if you want to go to visit to B, in a stack it's already available. In a stack that particular E is already available, so that I am not going to visiting B because the B is already available over here in the stack. So in fifth cycle there is no meaning to go with B, so it's nothing but fifth cycle I am just identifying that E. Why? Because from E there is no other path to move forward. Only thing is nothing but we can come backtrack, but there is no any forward path is not available, so that in fifth cycle I am closing that your E vertices is got visited. Means there is no further vertices to visit from E, so that I am just E is already visited. So what I am doing, E is get cancelled from the stack, means the E is going to be come out from the stack because it is already visited. So once the E is come out from the stack, what is the next stack is going to be available? D. That means we are coming backtracking. From D we have come back. So in D, is there any path is available to visit? Of course there is a path is available from visit from D, that is nothing but C, so that we can visit C. So what I can do, I can able to update my stack with C here. I will update my stack with the C here because there is a possibility to visit your C there. So on what cycle? On sixth cycle I am visiting C. From C, is there any possibility to visit anywhere? Of course, from C we can able to visit the C back, means it's nothing but the finishing time is also going to be in next cycle I can finish my C, so that by 7 I can able to visit. And after that from C, is there any possibility to go back? So there is no possibility to go back because is nothing but from C there is nothing to visit anything else, so I can able to cancel from the stack and it is going to getting popping out, so that this two position is get out, because just remember we are following last in first out. Then what is your last in is going to be getting available? That is nothing but D is going to be getting available over here. So from D anywhere we can visit. From D we can visit C, that is already popped out, and from D we can visit E, that is also already popped out. It is nothing is going to be getting available, so that there is no more movement of from D to go, so that we can able to close our finishing time of D with the 8 here. And after that from D there is no other hope to go, because so that we can able to cancel D, and D is also going to be popping out from the stack. So since D is also popping out from the stack, now what is the next vertices going to be available? B is going to be next vertices in the stack. So we can go back to B. From B we are checking out what possibility to we can move on. From B to D is already done, it is over, it is popped out, and B to C is also got popped out, and there is no other pathway to move on from the B, so that we can able to pop out the B also from the stack. We can close it, so that we can close our finishing time of the B is by 9. So now what is available, the remaining thing is going to be A. From A it's already all the vertices are get visited, and it is already popped out from the stack, and the final thing is nothing but A. So A is also got popped out from the stack. So this I am going to update with the defined time is nothing but finishing time of A is nothing but 10, and now we can able to see that the stack is become empty. The stack is become empty. So what is the meaning of stack is become empty? When the stack is become empty means it's indicate that we have visited all the nodes. All nodes are visited. All nodes are visited. That is the output of this particular DFS. So this is what the DFS says. And so what happening in the DFS, if you look at very closely, first we are starting with the A, and we are from A to B we are moving, and B to C, D we are moving, D to E we are moving, and after that still we are looking for anywhere to move, and see that it's going to D back. So after D there is nothing to move, and already B is already visited, and come back to E again. So what happening, we are doing a backtracking. Initially we are just moving on the forward direction, and after that we are going for a backtracking, and until what we can able to go for backtrack, we can do this backtrack until that particular backtracking vertices doesn't have any new path to explore. If there is no new path to explore, we can able to pop out from the stack, so that the stack is become empty in a particular point, and when the stack is become empty, it is indicates that we have visited all the nodes which is available in the graph. So this is what the way the DFS algorithm is going to work out in perfect way to see that all vertices which we are visited or not by using certain these procedures. So this is called the DFS algorithm. Okay. So next we will try to understand what do you mean by a BFS algorithm actually. Okay. So the BFS is also as like your DFS, Here also we are going to explore all possible nodes which is available in the graph to be visit or not. But in terms of DFS, what we try to do, we start with the initial source node. From there we are just searching in terms of the deep level or depth level by means of using the stack. But when we come to the BFS, breadth first search algorithm, this will be used to search the vertices in terms of the adjacency level or in terms of the breadth level of the graph, rather to go with the depth level of your graph. So in order to do so, this particular BFS algorithm is going to adopt the Q data structure, and the property of Q data structure is nothing but first in first out. Okay, and also the output of this BFS algorithm is nothing but forming of a tree, or we can say that a forming of a spanning tree. Means the output of the BFS is going to produce the visited vertices. At the same time, it's going to produce a tree through which we can able to see that there is no any loop or the path is not existing between the source node to the existing node, and that is what the source node to destination node. Okay, so that is what the difference where it is going to be getting differentiated between the DFS as well as in the BFS algorithm. So in BFS algorithm also having some certain rules and procedures. So where in step 1 we can say that define Q with the size of total number of vertices in a graph. So means indicates that what is the Q size, they says that the Q size is nothing but number of vertices which is available in the graph, means that much of vertices we can able to visit. So initialize the starting vertices and visit the other connected vertices into it, followed by updating the Q. Okay, we are initializing the starting vertices. Whether it is given in a problem or not, we have to cross verify. If it is not given, we can assume that, or we can able to start from any vertices. There is no any kind of thumb rule that we should not start from any, we should start with only a specific vertices. So unless in a problem, if it is not specifically given, we can we have a free handed to start with the any vertices as a starting vertices. But only thing is nothing but to see that from that starting vertices, are we following the adjacency vertices to be explored or not? That is the point. And step number 3, we can visit all the adjacent vertices. That is what I said. We can visit all the adjacent vertices from your source vertices, which is at the front of the queue and that is not visited, and insert them into the queue. Means we have to see that are that particular things available in the front of the queue. If so, then we can able to check out all that possible vertices are visited or not. If it is not visited, we will update the queue with the visited one. And step number 4, when there is no new vertices to be visited from the vertex at the front of the queue, then delete the vertex from the queue. So that we are trying to pop out the vertices which is already visited in terms of your first in first out priority, and accordingly we can able to make sure that the queues become empty in a certain point where when all the visited vertices are visited. So we can repeat this process, step number 3 and 4. This process can be repeated again and again until what condition? Until the queues become empty conditions, we can able to do so. And finally we can able to see that at the end of this particular step to step 5, we can say that the particular spanning tree is going to be getting formatted, and also we can witness that, and it is we can visited all the vertices which is existing on particular graph. So to do so, we will take this particular analogy problem. For example, we can take this particular problem, and accordingly we can able to move on to solve this particular specific one. See this here in this particular graph, they have indicated that S is nothing but 0. S is nothing but 0 here means that indicates that they want to start, the starting node of this particular graph is nothing but S is equal to 0, and the remaining things we are saying that it is going to become infinity, means we don't know in what position these remaining nodes of this given graph is going to be gets follows. Means it's false. In what level of the tree the given nodes are false, we don't know. So that's why we are writing in terms of the infinity over there actually. So now our duty is nothing but to forming the queue for this particular one, so that we can able to form a queue, and form a queue is nothing but it is just going to adopt the procedure called first in first out. It's adopting the procedure called first in first out. We will write like this, yes, first in first out. Okay. So what first in first out says over here accordingly, so I will just plot the queue here. We can able to take the queue here first now. So in Q I am starting with the S, I can say that this is at level 0. I am starting with the Q and this is at the level 0. I can able to say that. So we are starting with the node S, okay, and this is my level 0 is indicates over here. So from S, what are the adjacency nodes are available? For S, what are the adjacency nodes are available? One is the adjacency node is V, second adjacency node is U, and third adjacency node is T. Means what is adjacency nodes in the sense, like from S, what are the direct connection available? From S to T there is a direct connection, from S to V there is a direct connection, and from S to U there is a direct connection. Okay. So since we have direct connections with all these vertices, we can call this particular vertices are the adjacency vertices. So that we can able to update your Q with the adjacency vertices, so that I am just updating that as with V and U and T. So these are the adjacency vertices to the S in terms of the first level. So I am writing in terms of the first level, so that we can say that from S we have V, and from S we have U, and from S we have T. Okay. So this is my level 1 vertices or level 1 adjacency for my S, right. So now from S, is there any other adjacencies available? No more adjacency. So what we can do, we can able to pop out your S, so from your Q, so it is going to be getting popping out because it is first in first out, okay, not last in first out. Then what we can do, we can able to check the what is the first in first out. Accordingly we have V actually. From V, is there any kind of adjacency nodes are available, adjacency vertices are available? Of course we can able to check out it very closely. Yes, of course from V there is adjacency. What is adjacency is available? From V to U there is adjacency, but it is already visited. We have already available in a Q. And V to S is already V to S is there is an adjacency, but that is also already available and it is already popped out. And the next level of the adjacency for V is nothing but what? That is nothing but W. Already the V is in the level of 1, and from level 1 of V the adjacency of W is nothing but level 2. So we can write the next adjacency is going to W, that is nothing but from V. So from V I can able to write I am going to have a W. This is my level 2 level of adjacency, I can say, right. We have visited W. So now from V anything is available, anywhere to go available, so only W, S and Q already is got visited. So what we can do, we can able to pop out our V also from our Q, so it's get popping out. And what is the next is going to be U is going to be getting available. For U the adjacency is either S and T as well as V, but it is already visited over here, so there is no other place to move on from U, so that we can able to pop out U also from our Q. What else available? The T is available now. From T the adjacency are S, U and W, and S, U and W is already visited, so that there is no other further adjacency for T, so that we can able to close the T also from our Q. So what available in a Q now? In a Q it is available is nothing but W, and we see that from W is there any adjacency is going to be getting available. Of course there is an adjacency. One is we can go from W to T, or we can able to go from that W to X as well as Y, because we have an connectivity between W to X and we have connectivity between W to Y. But W to T is not possible. Why? Because it is already visited, so no need to go there. So from W we can able to go for X and Y. We can go for X and Y. This is my third level of adjacency, so that from W I can able to form X as well as Y. This is my level 3 adjacency get visited, right. So now we have visited X and Y from W. Now let me check, is there any other possibility to go for from W? So from W there is no possibility to move on anywhere, so that we can able to pop out W also from our Q. Now what is else available? Now X is available as well as Y is available. Now from X I have to choose X over here. Why? Because X is in the Q in the next things over here. So what happened now? Now from X where we can visit, now we can check out. From X we can visit W, it is already visited. From X we can visit Y, it is already visited. and from x what we can visit z actually. So for the x, the third level, fourth level, next level adjacency is nothing but z. So we can say that z, it is nothing but 4. So that from x we can able to form z. This is my level 4, we can say that. So once you have visited, then next is from x to y is already visited, popped out, and from y to w is already visited, y to x is already visited, y to z is already visited, it is popped out from the queue, and z, from z x is visited, from z y is visited, and this is also popped out from the queue. Now the queue is become what? The queue is become empty. The empty queue is indicating that it is already visited, means all the vertices are visited and there is no more vertices are pending on the given graph. And as we discussed in the early, that the BFS is going to follow forming a spanning tree. So this we can able to call it as what? A spanning tree. So where we can see that all the vertices which is available in your graph is going to be getting existing. There are S to Z vertices are available. All the vertices from S to Z is available in this tree also. At the same time, we are noticing that we have visited all the nodes without fails, and also it is not going to forming any loop, means we are trying to avoid any backtracking time scales, which we are just spending more on the DFS over there, and that is not going to be existing on the BFS. At the same time, the BFS is following the queue by means of following that first in first out procedure, through which we can able to exploring all the outcome of your BFS. So with this we are closing that conventional search algorithm, which we can use it for our which we can use it for our graph, so that we can able to verify whether all the vertices are visited or not, right? Thank you so much.